We start this part of the video with slide number 77. The relation between delta G standard, Gibbs free energy, and maximum work. You remember you had it in the previous chapter, and you just learned that this maximum work is minus NF E standard of the cell. So let's work on an example. The question on slide 77 says, calculate the standard free energy change for the net reaction used in the hydrogen-oxygen fuel cell. The reaction is the cell potential is 1.23 volts. How does this compare with delta G standard formation of H2O? So let's find out. We have to determine the number of electrons involved. So you see you have 4 hydrogen ions that are oxidized to hydrogen ion, and 2 oxygens are reduced to, so here you see hydrogen goes from 0 to +1, and here oxygen goes from 0 to -2. If you break it down to 2 half reactions, N is going to be, and try to balance it, N is going to be 4. So, and E is 1.23. So delta G standard for this cell is going to be minus 4 moles of electrons times 96,485 coulombs per mole times 1.23 joule per coulomb. So delta G standard is going to be minus 475, and you change it to kilojoules. And delta G standard for 1 mole is minus 285.8 kilojoules per mole. But you have 2 moles here, so you need to multiply it by 2. Is going to be minus 550 kilojoules, which is more than minus 475. Okay, now the next thing, question 70. Slide 79. On slide 79, a voltaic cell consists of 1/2 cell with iron dipping into an aqueous solution of 1 molar FeCl2, and the other half cell with Ag dipping into an aqueous solution of 1 molar AgNO3. Obtain the standard free energy change for the cell reaction using the, okay, I don't see any question in it, but let's see what's happening. Obtain the standard free energy change for the cell reaction using the standard free energy change for the reaction, and then the standard free energies of formations are given. What is the cell potential? Okay, this is the question. What is the cell potential? So the electrode potentials 2Fe, or we write it as this, is minus 0.41 volts. Ag plus Ag, E standard is 0.80 volts. Then more negative one is the anode, Fe is the anode, and silver is the cathode. So E standard is going to be cathode minus anode, which is 1.21 volts. Now, let's write down the half reactions. So now you can cancel the 2 electrons. You have Fe solid plus 2 silver ions gives Fe plus 2 Ag solid. And then delta G standard is going to be 1 mole times minus 85 kilojoules per mole minus 2 moles. That's what you find from delta G standard formations. 77 kilojoules per mole is going to be, delta G standard is going to be minus 239 kilojoules. Then now we can use from delta G standard is minus NFE. Then E is going to be minus 239,000 joules divided by how many moles of electrons did you have? 2 times F 96 for 85 coulombs per mole, and E is going to be 1.24 volts. So you see, these two values are very similar to each other. They compare very well. The last part of calculations you have on the cells is going to be on voltaic cells, on galvanic cells. I told you our focus is on this type of cells. We give you 2 types of equations, 2 types of formulas. E standard with the cell, you can calculate it from this formula. Or at 25 degrees Celsius, you can change this to, instead of NF, you can change it to divide 2.032 divided by F times RT. If you have at 25 degrees Celsius, then you will have 0.0592 divided by N logarithm of K. So based on this, we move towards this question. Calculate the equilibrium constant K at 25 degrees Celsius. So it means that we can use this formula. Calculate equilibrium constant for the following reaction for the standard cell potential. PB so we're dealing with an equilibrium now. Alright, so first we need to find the cell potential, right? Because we just need to have one unknown. E of cell is E standard of cell is a standard of But in the cathode minus E standard of anode, these will be given, or you need to find them from the table based on what you have. So you have 0.13 minus 0.41 again, minus. So again, you see the more negative is for anode. Negative, anode, both of them have N. So this is going to be 0.28 volts. Now plug it into this equation, ln K, log of K, can find it from both of the formulas. ln K that is given to you in the solution. ln K, the first before that, you can use this one also. Let's say log of K. And how many moles of electrons did you have? 2. So it's 0.0592. Go with the same formula that you have here, because it's happening in 25 degrees Celsius, divided by 2 log of K. Then K is going to be, if you solve it, 3 times 10 to the 9. That's going to be the solution. So you have a few formulas to work on slide number 86 that will be given obviously in the test. Now the last part is the stoichiometry of electrolysis. Electrolysis is the same that you will work on in your experiment. Stoichiometry of electrolysis. So, Michael Faraday needs to be given the credit for all the work he has done on the electrolysis and the charges and the flow of charge in a circuit. And he has found out that the total charge that flows in a circuit in a cell is related to the amount of the substance. So the amount of substance and the number of electrons can be related to each other. So what you need to know at this point is that electric charge is equal to current times time. And electric charge, its unit is in coulombs. Current is in amperes. And time is normally in seconds, unless you want it in minutes or hour. So on slide number 89, they're asking for what electric charge is required to plate a piece of automobile molding with 1 gram of chromium metal using a chromium 3 ion solution if the electrolysis current is 2 amperes. So we're using 2 amperes for 1 gram of chromium metal, Cr. How long does the plating take? So first we need to know what electric charge, and then how long does it take. So we said the amount of electricity depends on the amount of substance. 1 gram of chromium, and we know that 1 mole of chromium from periodic table is 52 grams. Then 1 mole of chromium, it says chromium 3, so it transfers 3 moles of electrons. 1 mole of electrons is 1 Faraday. 1 mole of electron is 96,485 coulombs. And the current, amperes, is 2 coulombs per second in 1 second. So the answer is going to be 2.78 times 10 to the 23rd seconds. If you change it to minutes, it's going to be about 46 minutes. That's how long it'll take. And finally, you have a solution of nickel salt. The last question you have at this point, you have slide 91. A solution of nickel salt is electrolyzed to nickel metal by a current of 2.43 amperes. If this current flows for 10 minutes, how many coulombs is this? How many coulombs is this? And how much nickel metal is deposited in the electrolysis? So we have 2.43 amperes, which is coulomb per second. Then we have 10 minutes. And you know that each minute is 60 seconds. So it will take 1,458 coulombs for this process to finish. Now we need to find out how many grams. So 1,458 coulombs. And we know that 1 mole of electron transfers 96,485 coulombs. Then 1 mole of nickel. Did it say anything about nickel too? No, but nickel transfers 2 moles of electrons. Then the half reaction according to that half reaction. And we know that 1 mole of nickel weighs 58.69 grams. So it's going to produce 0.443 grams of nickel. Okay, we reached to the end of the chapter based on what I have provided for you. We are not going to work on any more cells or any other calculations. The rest of the cells, you can, if you would like to read or know more about it, feel free to get them from your book. But that's enough as far as what you need to know from this chapter.